In this video, I'd like to review and contrast the examples of circular motion on an unbanked road and a banked road. As you can see from these visuals, there are cases such as those on the left where we rely upon friction to enable us to move in a curve. Okay, I realize in both cases we're probably not that trustworthy of friction and are likely wearing spiked or cleated shoes, but we'll ignore that. In each case, the runner is pushing outward on the surface, like this, and the surface then resists in the form of a frictional force acting radially inward. And that's what allows us to go around the bend. It provides that centripetal or radial acceleration. And if you've ever tried running in a curve while on ice or a pool deck, you know which way your legs slip if that friction fails you. So your legs go flying out that way. And so that tells you something about the direction of this force on you. It's acting radially inward in order to keep your legs from flying off in that direction. But if we're smart, we can bank the surface, like on the right, so that part of the normal force does the job for us. So if the surface is here, normal to that, we have a normal force, and there's a component that is working for us or does the job for us to act inward or keep us moving in a circle. And that is particularly critical on an icy surface, like for the bobsled here, where there is nearly no friction. And so you can see that the surface is nearly vertical in order to give as much of the normal force acting in the radial direction to keep us moving in that circle. Here's a sample problem for a banked curve, but in the process of solving it, I'll lay out both the unbanked and banked cases. The problem reads, highway curves are banked so that even if the road is extremely slippery, cars will be able to negotiate the curve without sliding. A, if friction is neglected, which force or forces provide the centripetal acceleration of the car? And what is the proper banking angle for a car traveling at 90 kilometers per hour around a curve of radius 500 meters? So the schematic on the right corresponds to the curved road up here on the left. The friction opposes any radial or outward movement in this direction. And without it, the car would slide radially outward into the guardrail. Let's look at the two scenarios now, an unbanked and a banked road, and their corresponding free body diagrams. So as the car pushes against the surface while churning, it exerts a force on the road, so the force on the road by the car here, and by Newton's third law of equal and opposite forces, we then have a force exerted on the car by the road. And this is a frictional force. It's a friction that resists the movement, and in particular, it's a static friction, or the force due to static friction. And so we know it'll adapt up to some maximum value given by mu s Fn. Let's look at the total forces that we have then. In the downward direction, we have the force of gravity. So that gravity is pulling us onto the surface. In the negative direction, and a magnitude of mg. And because it's pulling us onto the surface, we're exerting a force onto the surface, and the surface then exerts a force on us, or a normal force, of Fn. It's in the positive direction, and it's got a magnitude Fn. And the final force we have is the one that we said is that static friction acting to give us our radial acceleration. And that means that it will provide a velocity v for a given radius of curvature r, and those are our three forces acting on us. If we look on the left, I'm going to look at the components or the sum of the y components. I've got a positive Fn, I've got a negative mg, and there's no acceleration. So it tells me that those two are balancing each other out. Fn equals mg. And so that static friction will build up to some maximum Fs max given by mu s Fn. So when it's an absolute maximum. And so if I combine those two now, I've got an mv squared for my maximum velocity for that radius, and that's given by mu s Fn. And I can substitute in from the right for my normal force, so I've got mu s mg. And you'll notice then that the masses cancel out. The maximum velocity that can be maintained by that static friction is a mu s gr. On the right then, I've got now a banked road. And so like we did with inclined planes, I'm going to rotate my axes. And so I'm going to take my axes and I'm going to rotate them upwards to match the banking angle of the road. And if I bank my x-axis that way, that means I'm banking my y-axis with the same amount of phi here. So this becomes my new positive y-axis. And likewise down here, I'm banking the y-axis over there. And so that should be all of the angles I actually need here. Again, I have the force of gravity acting downward. So this is the force of gravity equal to a negative mg. And I have the force, a normal force, acting normal or perpendicular to the surface. It's perpendicular, always perpendicular to the surface. And the dashed line here represents the banked road. So it's going to be normal to that surface. It means then that there's a y component here that is balancing out the force of gravity. We'll get there. So that's my y component. And I'm going to have an x component here that is going to be an Fn sine phi. And I can show it down here instead, acting right at the center of my body for a free body diagram. So I've moved it down here and I have an Fn sine phi, rewriting it, and it's that Fn sine phi that is giving me my radial acceleration. If we look at the sum of the y components now, we've got an Fn cos phi minus mg all equal to 0. In other words, that Fn, that normal force, is now given by an mg over cos phi. And on the right, I'm going to rewrite this. I've got that Fn sine phi. That's the component of my normal force giving me my radial acceleration. So I know there's an acceleration. It's radially directed. And I can just make some substitutions then. So I've got mg cos phi for the normal force, all times sine phi. And on the right, I've got an mv squared over r. And I can rewrite this then. It tells me then that the maximum velocity that I can have based on that given normal component or component of the normal force and that given banking angle, where notice that my masses again cancel out. And so I can simplify this equation into gr tan of phi. So this is the maximum velocity without requiring friction. And this over here was the maximum velocity using that friction. I'm going to carry it over onto this page then for that expression, using that expression, but where I'm going to rewrite it in order to solve for the angle. So I now have the tan of phi is given by that velocity over gr, or that speed. And we're told here that it is 90 kilometers per hour. And we want to find the angle that allows us to do 90 kilometers per hour. And I'm going to convert that into SI units. So I know I've got 1 hour per 3,600 seconds, right? 60 minutes per hour and 60 seconds per minute. And then I'm going to times that and convert it to meters. So I've got 1,000 meters per 1 kilometer. That's how I do my conversions. And all of that is going to be squared. And I'll take that then over 9.8 meters per second squared times a 500 meter radius of curvature. That then gives me a value of 0.12755. And we'll have a look at the units. Notice up top we had a meters per second because my kilometers canceled out, my hours canceled out, and I'm left with a meters per second. But all of that was squared, so I have a meters squared per second squared. And on the bottom, meters per second squared times meters leaves me with another meters squared per second squared. So those will cancel out and I'm left with something that's unitless, which is appropriate here. And when I take the inverse tan of that, I then get a value of 7.268 degrees. In other words, to 2 significant digits as requested, I've got 7.3 degrees. This seems like a reasonable banking angle, so it's not too high, similar to the roads that we would see out there. And let's do a quick little recap then. On the left, we had the case of an unbanked road. And so here we were relying upon friction, so to provide or for that radial acceleration. And then if based on the maximum that we could get, so static friction will reach its maximum from when mu s is f, the static friction will reach its maximum given by mu s Fn, and that then tells us the maximum speed for which we could still maintain this radius r given a coefficient of static friction for those two surfaces. And those surfaces will, the coefficient will change depending upon the surface conditions, whether it's an icy road or a wet road, a slippery road. And so obviously we're at the mercy of that coefficient of friction and the conditions of the road. On the right then we have the case of the banked road, and here we now assume no friction. So we're building the banking so that we don't have to rely upon any friction. Then we end up with a maximum velocity that depends upon the banking angle. So we have a maximum velocity that lets us have that radius of curvature for a given banking angle. And now we don't require the friction. We're only relying upon a component of the normal force because of that banked road. And if we exceed that velocity, then we won't have enough to quite hold us into that radius of curvature, and we'll start to drift off towards the guardrail or the ditch. And so that's why now when you see the signs on the highway telling you a maximum velocity around those bends, it's based on the design of the banking angle and the radius of curvature. So maybe now you'll look a little bit differently at that speed limit when you're going out on the highway and you're making a turn on an off-ramp or around a bend.